All right, welcome back to another episode of Science with Surbeck. Today what we're going to be talking about is uncertainty in measurements and dimensional analysis. So, our objectives before we get going into the details of notes is number 1, determine the number of significant figures in a measured quantity. Objective 2, express the result of a calculation with the proper number of significant figures. And the third and final objective is you should be able to convert between units by using dimensional analysis. So we start off here and we get into these definitions known as exact and inexact numbers. And the definition for an exact number is known as a counting or defined set of numbers. And so it's easier to understand this in terms of examples. So one example is that 1 dozen is always going to equal 12 of whatever you're trying to obtain. Another example is the number 1 in conversion factors, such as 1 inch equals 2.54 centimeters. And so the biggest takeaway from exact numbers is that these will always stay the same. They're not ever going to alter or change. And so that's what we better mean by a defined number. Now, inexact numbers are derived from measurements. And because they are derived from measurements, they're going to have some uncertainty. And so this uncertainty that can come from this measured quantity can be from the equipment that's used to measure quantities, from human errors of how different people make measurements on a similar or the same device, and then they're always going to exist in measured quantities because of those above 2 factors. So because of these things in inexact numbers, this is why we have to have some way to communicate the significance of some digits in some measurements. So this is really the basis for why we have significant digits in our calculations. Now we'll get a little bit more into the details of how exactly or why exactly we have those the terms to be able to utilize significant digits. And so the first terms that helps us identify significant digits or use them is precision. And precision is just going to tell us how well measured quantities agree with each other. So a good example of precision, if you're throwing darts and you're missing the bullseye, but you're missing in that same exact spot, you are precise. Now you're not accurate, because accurate is how well measured quantities agree with the actual true value. So if we stick to that dartboard example, being accurate is hitting that bullseye right in the center. So something that's accurate is right on the true money, right on the true value. Something that's precise, over and over and over again, we get the same measurement. Now, in the laboratory, we have a couple things to be aware of. Number 1, we have multiple trials used for measuring quantities in the lab. So because we use multiple trials to measure in the lab, we have to take the standard deviation, or estimation of how far the average is used to reflect the precision of a measurement. And so if we're looking at the standard deviation, the goal is that we want a very, very small standard deviation, because that means it or we had greater precision of our measurements in our lab experiments. Now, there's usually 3 different types of generalized measurements in the laboratory. The first type of measurement is being accurate and precise. The second type of measurement is being precise but not accurate. And so this would usually happen when you consistently use an instrument wrong, or say, for example, a scale was not calibrated correctly, and you use that scale over and over and over to obtain those measurements of mass. Because you did that over and over and over again, you were precise but not exactly accurate to those true measurements. And then the third option is you're neither accurate nor precise. And usually in the lab, if you're not either accurate nor precise, you're really sloppy. You're all over the board when it comes to your measurements in lab. So because of that, because we have measurements and because those measurements are inexact numbers, we have to identify, well, what are the important digits or what are the significant figures in our particular calculations or our particular lab work. So with significant figures, all measurements that we do in the lab are going to have some degree of uncertainty or error associated with them. And so in measurements, it is useful to indicate the exactness of that measurement. And so exactness in our measurement is the number of significant figures. So we have some generalized guidelines for determining the number of significant figures in a measured quantity. The first guideline is that the number of significant figures is the number of digits with known or known with certainty plus one uncertain digit. So a good example of this is a measurement. If we throw something on an analytical balance and it reads out at 2.2405 grams, we know for sure that the mass is 2.240 grams. And so what I'm going to do here is on that balance here, we know for sure in purple, we know for sure that the mass is 2.240 grams. What we don't know, or what we're uncertain about, is this 10,000th digit here. We are uncertain about this value here. And so I'm going to box this in. This 5 value is what we are uncertain about, and that is to the nearest 0.000 gram. Again, we know for sure that we can lock in those values here. What we don't know is that last digit. So what the whole point of this is this. We know for sure 2.240, or we're certain on that. What we're uncertain is this last digit, and that is what significant digit is what we know for sure plus one uncertain digit there. Okay, so let's go through an example, and I'll have to walk you through this a little bit because it turned out darker than what I thought. Okay, so what we have here is we have our graduated cylinder, and I darken this in, but I'm going to guide you through this. So the graduated cylinder is regulated or has marks every 1 millimeter. And so on this particular diagram, I know for sure that it is above 19 but below 20. So because that meniscus is above 19 and below 20, what I'm going to do is I know for sure that there are 19 milliliters. And again, what I'm going to do here is I'm going to estimate one past what I know or what I'm certain of. So I'm going to estimate this to be 19.2 milliliters. Again, the 19 right here is what I for sure know, or we call that our certain digit. The 0.2, and I'll box in here, this is what I'm uncertain about. And so that is that one uncertain digit. So again, always estimate what you know plus one digit that you're uncertain about. And that's really key to be able to get significant digits correctly. Now, what we're going to shift gears to is the certain rules that we have in place with our significant and or our uncertain and certain digits that we call as significant figures. All of these calculations stem from being able to measurements, and it's because we have that uncertainty. This is why we have to develop these rules for this process here. So we will shift gears and we will shift to counting significant digits. The first rule about counting significant digits is that non-zero numbers and zeros between non-zero numbers are always significant. So an example of this rule right here would be 1,005 kilograms. So again, 1,005 kg, because those zeros are smushed in between a 1 and a 5, there would be 4 significant digits. Now, the next rule here is that zeros before first non-zero digits or leading zeros are not significant. So an example here for this particular rule. One, if we have 0.0026, these first zeros, because there's nothing beforehand, they are not significant. So we don't start counting until we reach that first non-zero number. So here there is only 2 significant digits. Now, our third rule is that zeros at the end of the number after a decimal point, and again, after a decimal point, are significant. So an example here, if we have the value, if we have the value of 1.4100, because we've had a significant digit and a decimal, these zeros count. So right here, there are 5 significant digits. Okay, and then the zeros, our fourth rule here, zeros at the end of a number before a decimal point are ambiguous, or they don't count. Now, this fourth rule is a little bit weird. So what happens is that exponential notation or scientific notation is going to eliminate this ambiguous or ambiguity here. So, for example, remember, if we have that decimal point and those zeros are after a significant digit and after the decimal point, we can count them. So I have 2 quick examples here, both dealing with the same number, but option 1, we have 1.03 times 10 to the 4th grams. This right here, this has 4 significant, or excuse me, got ahead of myself, that has 3 significant digits. Now, if I go ahead and I say there's 1.030 times 10 to the 4th grams, there are 4 significant digits. So to help avoid counting versus not counting the zeros, you can put it into scientific notation. Now what we are going to do here is we're going to shift gears and we're going to talk about the rules that are applicable for calculating our significant digits. So the first rule that we get into when we calculate significant digits is this: the least certain measurement limits the certainty of the calculated result. So what this means for us is that the answer is reported with only one uncertain digit. So we have to limit ourselves to that least certain measurement. The second thing is that in an addition or subtraction, we need to report the least number of decimals. So an example of this is if we took 20.4 grams and we subtract it from 1.322 grams. So again, 20.4 grams minus 1.322 grams. Now, you could do this calculation, and I'm assuming you could probably follow the rule, but a really easy way to do this when we add or subtract, anytime we add or subtract, we take 20.4 and then I'm going to subtract it and I'm going to line up the decimals. So I'm going to take 1.322 grams, and what I'm going to do first is I'm just going to throw these numbers into my calculator. So if I do this, 20.4 minus, if I do 20.4 minus 1.322, what I get here is 19.087. And for right now, I'm just going to write that down, 19.078 grams. And now what I do, I have everything lined up really nicely, is I do this. I find the least number of decimals, which is 20.4, and to the right of it, I draw a dotted line. So that means I can only report this particular value to the left of my dotted line. And so we're getting a little ahead of ourselves, but this would round up to 19.1. So that would be our value for that particular problem. Now, for multiplication and division, we need to report to the least number of significant digits. So again, let's go through an example here. And so let's say we take 6.221 centimeters and we multiply it by 5.2 centimeters. Now, what I'm going to do here is I'm going to, again, just plug these numbers into my calculator and I'll put the entire answer, and then we'll talk about some rounding here. So we have 6.221 times 5.2, and we get an answer of 32.3492. Again, this is 32.3492. This would be squared centimeters. And then we need to talk about, well, where do we round? Well, we count our significant digits. And so this right here, 6.221, has 4 significant figures or significant digits, and 5.2 only has 2 significant figures or significant digits. So that means our answer can only have 2 digits or 2 significant digits. So this right here, because we have 32.3, would actually round to 32 and you can leave that decimal. Make sure you don't put a 0, but 32 squared centimeters. Okay, so we have this. We need to talk about rounding, which I already got into the business here, so I'll just quickly go over those rounding rules. We'll try out a calculation, and then we will go to our last portion of these notes. So again, just transitioning to rounding our significant figures. We've already gone over this, so we're just going to make sure we formalize our answers. One, what you need to do is look at the numbers to the right of the last significant digit. And so if that number to the right of the last significant digit is less than 5, the number is left as is. So in an example here, let's say we have the number 7.248. So we have the value 7.248, and we want to round to 2 significant digits. So again, I'm going to say round to 2 SF for significant figures. Again, we want to round 7.2. We look to the right. It is less than 5. So what this rounds to, I'm going to draw an arrow. What this rounds to is just 7.2. Now, if the digit is 5 or greater, the number is increased by 1. So an example here, let's say again we have the number 4.735. So we have 4.735, and we want to round to 3 significant digits. So I'm going to say to 3 SF for significant figures. That number, because we're rounding to 3 digits, because this is a 5, it would increase to a 4.74. Now, there's one major exception here, and we don't see it very often, but say we're rounding to 3 sig figs, and we have 50 behind it. That means it's exactly at 50, so the number actually stays the same. Some rare circumstances here. We'll work through those if we end up there. So one important thing to remember is this. In multiple step calculations, always retain an extra significant figure until the end to prevent rounding errors. So again, in multiple step calculations, always retain that extra significant figure to prevent rounding errors, and that is to the end. All right, so what we'll do here, the text is a little small here, so I will zoom in, but we want to use our significant digits to answer this question. So a gas at 25 degrees Celsius fills a container whose empty volume is 1.05 times 10 to the third cubed centimeters. The container plus the gas has a mass of 837.6 gas. The container, when emptied of all the gas, has a mass of 836.2 grams. We want to know what is the density of the gas at 25 degrees Celsius. So the first thing that we have to do in this particular problem is we have to figure out what formula we're using, and it is the density formula. And so we need mass divided by volume. Well, to get to mass, we actually have to do a little work on the side, and that work is this. We need to take the total mass and subtract out the mass of that empty container because we just want the mass of the gas. So we take 837.6 grams and we subtract it from 836.2 grams. And again, what's nice about this is that both of these have the same digit. I assume they were measured on the same scale, I'd hope. And so we go to the one with the least significant decimals or the least number of decimals, and we draw that dotted line. Again, this is really nice because what that means for us is that we can just plug in the calculation and round, as we'll see. So all I'm going to do here is I am going to plug in 830 or 837.6 minus 836.2. And so when we do that, we get a value of 1.4. And so we say, okay, 1.4 grams, we need to have just one decimal, and that works out really, really nice because it's one decimal. So our mass, when we go to calculate that, our mass is 1.4 grams, and then it's divided by the volume of the container, which is 1.05 times 10 to the third cubed centimeters. So 1.05 times 10 to the third cubed centimeters. And so again, what we're going to do is this. I'm going to take my value 1.4. So 1.4, and I'm going to divide it by 1.05 times 10 to the third. Notice how I put what I have in scientific notation in parentheses. Then I press enter. So we have, and I'm going to write some extra digits down. We have 0.001333. And I kept quite a few more digits than we need. So now we turn to, well, what do we round to? Well, we did a division here, and so the rules for the division is that we round to the least number of significant digits involved in that calculation. So 1.4, this guy has two significant figures. 1.05. Now in scientific notation, we don't count the times 10 to the 3 business, just what's in front. And so this right here, 1.05, is 3 significant digits. So the least number is 2, and so that means our density, when we round it correctly, the density is either 0.0013, because that 3 does not cause it to round it, grams per cubed centimeters, or remember that ambiguous portion can be eliminated if you bring the same exact number. And all I'm going to do, I'm just going to bring it into scientific notation, and we eliminate this. So we said 2 significant digits. Well, look at this. 1.3 times 10 to the negative 3 is that same exact thing. And it makes it a lot easier because we can just have that number there. Either of these answers are correct. I would accept either of these answers. But remember our rules that were involved in this particular calculation. Okay, so we have just one more major section here, and that is going through and using our dimensional analysis to get to some answers. So we'll go over some basic rules and regulations, and then we will transition to actually doing some problems. So we get to dimensional analysis, which we started to do in the previous day of notes. And so with dimensional analysis, we have a couple of things here. Number one, it's just a method of calculation utilizing a knowledge of units. So it's just saying given units can be multiplied and divided to give the desired unit. Now, something key with dimensional analysis is that it's going to use conversion factors. And all conversion factors are simple ratios whose numerator and denominator are the same quantity expressed in different units. So a key thing with a conversion factor, and we can just go through a generic example here, is that you get the conversion factor, and how we set this up is that we have the given unit on bottom, and on top we have, or we get to the desired unit. And so an example of this, a real world example, is a conversion factor from inches to centimeters. And so 1 inch is equal to 2.54 centimeters. So how we set that up is that 1 inch is equal to 2.54 centimeters, and that's how we would express this particular conversions. Now, another thing to note is that multiple conversion factors may be used in one-dimensional analysis question. So the last thing that I want to go over on this page is just some generic guidelines for using conversion factors. The first guideline is that diagonal units have to cancel out. Again, diagonal units have to cancel out. So to express this in a generalized answer or a generalized example here is this. We have our given units, whatever we're given in, our given units have to cancel diagonally. So when we set up that conversion factor, we have the given units on the diagonal portion and then the desired units on top. Now, the other thing is this. Units in answer and throughout the conversion factor must be included. Okay, so let's put our knowledge here to the test with some example problems. So we may, and you may need to reach back to the previous day notes to get out those metric conversions. So problem number 1, if a woman has a mass of 115 pounds, what is her mass in grams? The nice thing here, I included 1 pound is equal to 453.6 grams. So what we do, we always write down the unit and value that we are given first. So if I zoom in here, we start out with this woman and she has 115 pound mass. Now, the way we set up the conversion factor is we set up a times, and it looks like a fraction almost. So this means that pounds, LB, has to be on bottom, and our desired unit is in G4 grams. All we have to do from here, once we have the correct unit plugged in, is plug in the numbers. So this conversion right here that's given, it says 1 pound is equal to 453.6 grams. So all we got to do is multiply this out. So what we're going to do is we're going to take 115 times 453.6 all divided by 1. So in my calculator, what I'm going to do here is I'm going to have 115 times, I'm going to have times 453.6. I'm going to multiply this out. Well, this equals 52,164 grams. But we're not quite done. We must round this to the correct significant digits. So if we look back, 115 has 3 significant digits. 453.6 has 4 significant digits. Because we multiplied or divided here, we go by the least number of significant digits. Least number is 3. So that means we look back here. That means we can only have anything to the left of 1 and left. The 6 says, hey, you must round. So this actually becomes 52,200 grams, all because we need to include significant digits. Now we move down here. The average speed of a nitrogen molecule in air at 25 degrees Celsius is 515 meters per second. We want to convert this speed to miles per hour. So what we're going to do first is write down the speed that is given in the particular unit. So we have 515 meters, and I'm going to do something different. I'm going to draw per, but put second on the bottom. So we have two conversions that we need to convert to. The first is I am going to go and get rid of meters and try to get it in miles. If you notice, this is 1 mile equals kilometers. So what we have to do is this. We have to look on our sheet and we have to find meter and kilometer. So kilometer has the unit of 1 times 10 to the third base units. So what this means here is that 1 times 10 to the third base units, which is going to be a meter, is going to be equal to 1 kilometer. Okay, so we first have to convert to kilometers. So what this means is that we have to have units of meters down in the bottom right, and then units of kilometer in the top right. And again, what we need to do is we need to take 1 times 10 to the third meters for every 1 kilometer. Now that we're in kilometers, we can convert to our miles. So down here, we want to knock out km. Up top, we want to put m for miles. 1 mile is equivalent to 1.6093 kilometers. So we can do one of two things. We could calculate this out, but we'd still be in miles per second. What you can do, and you can do that, but what you can also do is keep going. So now we got to get rid of seconds and we got to make it into hours. So this time we've been cross-canceling down and diagonal, but we can also cross-cancel up and diagonal. So S is going to have to cancel out. Now, we could go straight to an hour, but I want to make sure that we know how to get there. So I'm going to first go to minutes because that's the next timing unit that we could use. So we need to establish how many seconds are in 1 minute. So 1 minute equals how many seconds? 60. So 60 seconds in 1 minute. So you have 60 per that 1 minute. And we're still not in hours, so we have to do one more thing. Again, cancel up, kind of a weird deal, but we have minutes. And on bottom, what we have is hours. Now again, how many minutes now are in 1 hour? So 1 hour, 60 minutes. So 60 minutes to 1 hour. Now what we have to do is this. What I like to do is I multiply everything on top and then I divide it by everything on bottom. So on top I have 515 times 1, which I'm not going to show, times 1 again, not going to show, times 60 times another 60. Now I'm going to divide this number and it says answer. I'm going to put a set of parentheses. That is very key. Set of parentheses around 1 times 10 to the third. And notice this. I put another set of parentheses around my scientific notation. This gets multiplied by 1.6093. And I close my parentheses and I press enter. When this number pops out, it gives me a value of 1,152.05 miles per hour. So again, I'm going to write that down, but we have to do some rounding. So this is 1,152 1.05 mi per HR, or miles per hour. Now, we must round correctly. Well, the only unit that was not a conversion factor was this 515. So that means we need to, because 515 has 3 significant digits, we need to round this to 3 significant digits. So we look at our third digit, we look backwards, it does not round. So this becomes, the movement of this nitrogen molecule becomes 1,150 miles per hour. Now you could also express this in scientific notation, but to save some time, I'm just going to put it as 1,150 miles per hour. Now, we have Earth's ocean. It contains approximately 1.36 times 10 square kilometers of water. Calculate the volume in liters, and we have a conversion factor here. So what we have to do first is write down what we are given. So we are given 1.36 times 10 to the 9th square kilometers, and this is going to come into factor. The first thing here is I got to get it into meters. So I got to go kilometers to meters. And so what I need to do is this. I need to look up, okay, how many meters are in a kilometer? So again, if we look up here, there are 1 times 10 to the third, 1 times 10 to the third meters for every kilometer. So I just plug these numbers in. So 1 kilometer is 1 times 10 to the third. Now, we have to hit the pause button here because we have to cube this. Notice how this is km and this is km cubed. What that means is we need to cube our conversion factor. Okay? So that will be key as we multiply this out. The last thing that we need to do is this. We need to take 1 times 10 to the negative third. Oop, gave that away. We need to take our unit of meters cubed. And now because we cubed this up top, we already have meters cubed, and then we can get to liters. So because we have this, again, I gave this away. This should be 1 times 10 to the negative third for every 1 liter. We don't need to cube this because meter cubed now cancels out with meter cube. The only time we need to is if these don't match up like we had at the start. So now comes our calculation, and this is really, really critical here. So what we're going to do here is this. I'm going to have 1.36 times 10 to the 9th. I'm going to close the parentheses. Then I'm going to multiply it by 2 parentheses. 1 times 10 to the third. So 1 times 10 to the third. Then what I need to do here is I'm going to cube this. So how I cube it is I hit this little root symbol, cube it, I close the parentheses, and then what I do, notice how I just multiply by 1, I hit enter, and it's a really big value. Now I still need to divide by 1 times 10 to the negative third. This is not cubed, so what I do is this. I divide by 1, and I'm going to put a double set of parentheses. I divide by 1 times 10 to the third, negative third, and I get my answer. So my answer, unrounded right now, unrounded is 1.36 times 10 to the 21st liters, and I have to double check. To make sure my significant digits line up. Again, the only number that wasn't a conversion factor is this 1.36. That has 3 significant digits. That means my answer needs to have 3 significant digits. So how we wrote it is correct because that has 3 significant digits. All right, so I know that's another long episode, but I hope you have enjoyed yourself as much as I have. Always remember to subscribe.